what we covered last lecture. So we talked about closed sets. And remember, we gave the definition and then we gave characterization. We said that A is closed if and only if A is, if and only if, let's say, A contains all the limit points. Let's say it like this. A contains all of its limit points. So simply, what A touches is his. Okay, and we also had this, we then mentioned that A prime, this means limit points of A. So A prime is the limit points of A. That means just points that are in immediate vicinity of other points of A. And then we define the closure of A. Remember what closure was? So the closure of A, also written as A with horizontal bar on top. This we saw, it's not the definition, but we saw that this ends up being equal to A, and all we have to throw in are the limit points. Okay? And from there it's clear that A is closed if and only if A is equal to A union A prime, which is then the same thing as saying that A has to equal to the closure. So the definition of closure was we take A and we encapsulate A within a closed set that's slightly bigger than it. And then we take the intersection of all closed sets that contain A. This will be the smallest closed set that still contains A, and that's A closure. And this is a difficult characteristic. It's much simpler to just say, throw in all the limit points. Good? Throw in all the limit points, and what you get a predatory set. You get a closed set. So that was about A closure. How about A interior? So remember that A, that's one thing that we mentioned, and we can say that U is open. Open if what? If X belonging to U implies all of radius epsilon around X is inside U for some epsilon. So then we define the interior of A. And that's simply written as A with this degree sign. And that means the biggest open set or open subset U of A. And what's the easy characterization of A interior? This is simply what? Simply take the union of all the points A where A belongs to A and a ball of radius epsilon around A is also inside. In other words, A interior just gather the members of the herd in A that are protected by bodyguards, fully protected, have a full neighborhood that defends them. Okay? And what does that amount to? So if I take A, clearly you see, by the definition, to make it an open set, I need to maybe give up some points. What are the points that I must give up? Can you guess? What points do I give up so that A is an open set? No, limit points might be well protected. Right? So you think about a picture. You can think of a disk here. So when you said limit points, think about a disk. This is an open set, correct? And this guy maybe is a limit point of a bunch of elements of the open set. Why do I need to give him up? He's defended. So no, not the limit points. What do I give up?
Any of the points you cannot generate an open ball around?
Exactly, right? So A, just remove from it points that do not have an open ball around them. A is such that ball of radius epsilon around A intersects A complement for all epsilon bigger than 0. So those are the points that just cannot possibly be protected. There's nothing I can do for them, so goodbye. I lose them, and what remains is an open set. It could be that I have to lose every single point. There is no problem. If I lose every single point, the empty set is open, correct? And the empty set is closed. There is no contradiction. It's both open and closed. Okay? So we understand what are interiors and what are closures. Perhaps maybe, let me see if I have a few examples to make sure that you have it well in your mind. So, example. In this example, we take so we take R to be the space, and the absolute value to be the usual metric. Okay, we'll take first this to be the metric space, and then within that metric space, we will consider, tell me please what is the interior of the interval 0, 1. What's the interior of that equal to? So you see, again, if I just ask you what's the interior of anything, that makes no sense. I must have an underlying metric space. I must have an understanding of what's the universe. Yes, please?
It's going to be from 0 to 1, excluding 0 and 1.
Yeah, so 0 is already excluded. In this case, I must give up the point 1. Because why? 1 is not defended from the right. Predators on R can approach and touch 1 from the right, so I must give it up. Every other element is fully protected by bodyguard of elements from 0 and 1. Yes? So that's in R. B, what will happen if let's say in A, what happens if I take the closure first? The closure of the set 0, 1. What happens to the set if I were to take the closure? In the same space, what is that? Yep.
Include 0.
Include 0. Now it's closed. You can see this is a closed set. You can see why did I include 0? If this were a closed set, it will have to eat its limit points. In the last lecture, we saw that's fully enough. As soon as the set consumes all the limit points, it is a closed set. The only limit point not inside the set is 0. By the way, what is the set of all limit points for this interval? If this were A, what would be A bar? If I were to say, here, let me write it down, just to be sure that you are on the same page. So what if I were to do this? And I have this bar, so by that I mean limit points. What will I what will I have obtained?
The interval from 0 to 1 including 0 and 1?
Yes, I would have obtained the same thing as what I have for closed sets. Every point here is a limit point of the set. The only one not in the set is 0. Okay? Good, wonderful. So I hope this is simple. Now, in this example, what would be the interior of the set 1 over n, where n goes from 1 to infinity, right? If I just list through all those, if I go through all those points, if I take the interior, what do I get?
Open.
Well, so remember what interior is. You look at the set and you ask which among the elements of that set can I fully defend by an open neighborhood? And the answer is, who can I defend? Remember what you do with interior. Interior, you have a herd, you can only thin the herd, you cannot increase it. That's what you do when you take interior. You take the biggest open subset inside of it. What could it be? Yep. Just one what? Just the number 1?
Yeah.
But how is 1 defended? Okay, if you don't see it, let's try to draw those points. Again, how does the sequence look like? Well, the sequence looks like this. So this is the point 1, then this is the point 1/2, then somewhere over here is the point 1/3, then etc. Right? The points get close to one another, but there is always space between them. Is any of them protected? In other words, can I create a neighborhood around, let's say, 1/2? That will be defending 1/2. And that, in essence, a neighborhood that only contains members of rational numbers of the form 1 over n. No. So 1/2 is indefensible. Is 1 defensible? No. Is any of them defensible? Can you see rigorously why not? What you do is between each, there are decreasing sequences. Take 1 over n, take the distance to the closest, take the distance to 1 over n plus 1. That would be the distance to the closest, right? So the answer is the empty set. Do you agree? Nothing. In other words, I have to give up every single point to make it an open set. That still is an open set. Still a subset. Nothing else, right? No one is defensible. Because here, if you don't see it, I'll erase this part. So what you can do is you just take the element 1 over n and ask, can I defend it? So what you do is you take the distance epsilon, and you take epsilon to be equal to 1 over n minus 1 over n plus 1. Right? So that's the closest guy to it. So if you take a ball of that radius, that full ball contains no friends, nothing. Is alone. So in a way, 1 over n is a discrete, it's a discrete subspace of, although the distances, they decrease between them, but it's discrete because everybody is isolated away from other members of its species. So that's the empty set. You wanted to say something?
Yeah, so if you use the discrete metric, then all of them would be protected.
Wonderful. If you use the discrete metric, we're going to ask this. So I'm going to actually make sure that we're going to change a few things here, and we're going to see how that might change, even with the same examples. You have to just play around with basic examples to get what's the idea here, right? So B, nothing. What would be the closure of the set? The closure of the set 1 over n. What would be the closure, please? 0 to 1, you're feeding way too many points to this thing. Closure is smallest closed set. So this is a sequence. Can you imagine it? The sequence, just 1, 1/2, 1/3, etc. It's just a bunch of points. What must you feed?
To close it, you need everything in between, no?
Why?
You need to protect them.
No, that's to make it open, right? Closed sets don't care about protection. They just want to what? They want to eat everything they touch. What does the sequence touch?
Didn't you say that a collection of individual points is always a closed set?
A finite collection of points, yes,
Right.
but this is an infinite collection of points. Remember, so you can prove that if you take in any metric space, if you take a set that contains only finitely many points, it's a closed set. Now, why? Viscerally, why? If you have finitely many points, they cannot approach, they cannot touch anything. So you don't need to feed any limit points. Do you see the strong connection to limit points? No. A set is closed if the complement is open, which means that if a point is in the complement, it's protected by the set. Which means that whatever point is arbitrarily near the set, it has to be part of the set if it's to be closed. And what does it mean? The arbitrary near thing is limit points, right? So a closed set is one that feeds on limit points. It eats all the limit points. That's all that matters. That's the example of the blob. If I touch something, then I eat it. It's part of me.
So what are the limit points for set?
What are the limit points of the sequence 1 over n? What points are arbitrarily near points of 1 over n?
0.
0 and nothing else. The sequence converges to 0, so it touches 0 alone, nothing else. So the closure of the set, all I need to do is I need to add 0 to the set and take the union with 1 over n, and there we have a closed set. So I see very sad, droopy faces. Something is not right here. Are you with me, guys? You follow? In your head, I explained it a few times, but in your head, do you understand why a closed set feeds on limit points and why that's sufficient to be a closed set? Just go through the definitions again and again until that becomes obvious. A closed set has an open complement. That's the definition. A set F is closed if the complement is open, which means every point in the complement is fully protected away from this terrible guy, defended by a bubble or up, whatever, by a soap bubble. I don't know how you want to view it. There is a protection, and that soap bubble contains members of its own kind, of the complement kind. Okay? So that means what about this guy? It means that whoever this guy came close to, whatever point he came close to, he has consumed it. He has appropriated this point within itself. So closed sets eat limit points. They incorporate all limit points. So if that's this condition. So when I make the set closed, I must feed all the limit points. What are the limit points? They are the points that if you select that point and draw any neighborhood of any radius, you will see infinitely many members of 1 over n. If you take, that's what we showed here, that's why the interior was empty. If I take any point of 1 over n, you can see that there is space between them. Take any point other than 1 over n and other than 0, you can then see that there is space between them. Right? The only place where they gather, they are all, it's Cauchy sequence. The Cauchy sequence can only have how many limit points? Only 1, at most. Why? Because Cauchy sequence, they cluster. They essentially look like finitely sparse points, and in some place all of them are gathered. So they gather around 1 point. Okay? So closure is this. So what else do I need to ask you? Well, let's ask, so what is the set of limit points of that set? The set of 1 over n limit points. If I take this thing, if I take this operation, what are the limit points? We just mentioned it a moment ago. How many limit points do we have? 1, which is 0. Okay, good. Now let's change this slightly. Will you remember those definitions? I can erase it. So now let's change this example. I'll do 2 changes of the same example. Same exact thing, we go through the same exact procedures. Now what I have is, actually this is B. Let me also ask you about C. So I take Q, and I want to know what's the interior of Q. The interior of Q is, in that example, interior of Q. So in other words, I'm asking which elements that are Q, that are rational numbers, can be defended. And what does it mean to be defended? I pick a point. I pick an arbitrary point in Q, and I try to select an open neighborhood around it. Will this open neighborhood contain only rational numbers? No. Why? Because you can just as well show that real numbers, irrational numbers are dense within a number line. I think that was one of the homework assignments. You can play around with 1 over root 2, for example. Take 1 over root 2 and multiply it by a small integer. That will make it very small. Okay? You can shove in and just shift it around. You can quickly shove in irrational numbers between, or maybe root 2. I can show you how to do it. You can shove in irrational numbers in between any two real numbers. So this must be empty. What is the closure of Q? In other words, now think about it carefully. What are the limit points of rational numbers in R?
Irrational.
That too, but everything. Right? Well, how do you know? Well, remember what we showed. We showed that between any two numbers there is a rational number by Archimedean property. So what you do is pick, first of all, closure will contain all of Q, but regardless, pick any point and select an interval around that point. So this interval contains one real number and another real number. Between them there must be a rational number. What does it tell you? It tells you that every neighborhood of any number is infiltrated by Q. And that means every point is a limit point. And that tells you that if you want Q to be closed, you have to feed it everything. So it has to be R. Make sense? You understand why the interior is empty. What is the limit point of Q again? We just mentioned this, that's how I figured it out. The limit points of Q are R. It infiltrates any neighborhood, so it's arbitrary near any point in R. This is going to be, I'm hoping this is simple enough, guys. I'm afraid you follow, right? This is just, all I'm teaching you is really how to play with those symbols. It should be based on, well, how do I know that this is empty set? Because, well, because I can try to create an open interval around any point in Q, and there will be irrational numbers in that interval, and that can be shown just as you showed that rational numbers are dense, just the same idea. Alright, so let's try to do the same example, but in this case, what we have is, in this case, our space M is simply the interval from 0 to, let's say, to 2, and not including either 0 or not including 2, so, and the distance is still the same distance, okay? And now we try to answer the same question. So in this case, what is the interior relative to M? Of course, you might emphasize it's relative to M of the interval 0, 1. What's the interior? The same. The interior is the same as before. What about the closure? What is the closure of that set?
You can't close it.
Well, in that set, you can always close relative to that set. Relative to any metric space, that's your universe, of course you can close.
The same as itself.
The same as itself. You just feed the limit points, but 0 is not the limit point. It doesn't exist. This is just, again, artificial. It doesn't exist. There is no 0. There is no 0. There is no limit point. Here there used to be one. Here, no. There just, there's nothing there. Yes? Well, it's easy to answer what's the set of limit points. So 0, 1, set of limit points. Again, when I mentioned that's relative to f, always relative to the universe. The set of all limit points is the same as the closed set of this. Yep. And everything else, this is what's going to be b. B, the interior of 1 over n, will be what? Any difference than before? No. All the same. No point can be protected, but is there any difference between the closure?
Yeah.
The closure of 1 over n is what?
1 over n.
Exactly. So what can I conclude about the set 1 over n? The set of 1 over n in this case is closed. You see, because why wasn't it closed here? Here was a missing point. Also, if you notice what happens here, this is a case where 1 over n is Cauchy, not convergent. So this sequence can only have at most one limit point, but it has none in that space. So it's a closed set. Okay? What's the set of limit points? What's the set of limit points? Empty. No limit points. Wonderful. All right. So this is changing this example A and B. Now let's change it again slightly. You already know the answer. So now I'm going to say this is going to be R discrete. R discrete. And I'm going to ask again. In R discrete, what's the interior of 0, 1? The interior of 0, 1 is the same. What's the closure of 0, 1? The closure is what does discrete mean? It means that now I say that the distance between any two points is 1. So if the point is not the same, the distance between one and the other is 1. If I take the same point, the distance is 0, of course. So the distance of a point to itself is 0. The distance of a point to another is exactly 1. So that's called discrete space. For very clear reasons, if you kind of see what are the open sets, right? So what's the closure of 0, 1? What is the closure? The same. Because the complement is open. Every set is open, therefore every set is closed. Same. What's the set of limit points? What's the set of limit points? Sorry? None. It cannot have any limit points. Why? Because limit points means that you can get arbitrarily closed or something, but how? Right? Take any point. Any point, you can always select a neighborhood where epsilon is 1 or smaller, where the neighborhood contains nothing but that set. So you cannot sneak up on any element. So it's empty set. Okay. And what would be the case with B? The case with B, where if I take 1 over n, what's the interior of 1 over n? Itself. Is there any case where the interior will be any different from itself? Would there be any subset of R where the interior of that subset is smaller? Can you find some subset A in R that has a smaller interior? This is R discrete. give me an example of a subset of R. And if you take its interior, you will have a smaller set. The interior is smaller. It's not discrete. Can you give me such an example?
Every element is its own open ball.
Right.
So no.
So the answer is no. You cannot give me such an example. It doesn't exist. So the interior of 1 over n is 1 over n. The closure of 1 over n is what's the closure?
The same.
Same. What are the limit points of 1 over n? None. Empty. Good? Right, so just quickly let's write C. I'm hoping it's boring you. So Q interior will be what? Q interior in this example, R discrete, is Q. So you understand why. Every single point is its own open ball. And therefore, I can express any set as the union of arbitrary many points, and therefore every single set is open. And therefore every single set is closed, because it's a complement of some open set. Okay?
So are you trying to say in a discrete space, every interior enclosed set is itself?
Yes, they don't do anything. They're trivial operations. They never do anything in a discrete space. Closure never does anything. Interior never does anything. Are there spaces where the interior is bigger than the set? So is there some magical metric space where I can find a subset A, and I take its interior and it's bigger than A? I'm just checking if you remember. Obviously not. Interior, by definition, is open subset of A. By definition, it's not possible. Okay, when you take interior, you, by default, lose points. Maybe you lose nothing. If it's an open set, I don't need to give up anything. But in interior, potentially means I have to give up everything. Closure, I gain things. Closure, I fit the set to make it closed. Okay, so this is Q, and then if I take Q closure, I don't change anything again, I get Q, and if I take limit points of Q, I get the empty set. That's why it's called discrete. You cannot really sneak up on it, on any creature in that space. Make sense? So you will see when we speak about connectedness that discrete spaces are important. So you can prove a lot of important theorems, some of which are occupying and torturing me, related to discrete spaces. So maybe one more example. And mostly I'm giving you R, but you can have all sorts of spaces. So I take R, and let's say I take, so it's R regular, and let's say that we have Rn, where this is just a countable set. So I'm just taking some countable set in R. It can also be R2 if you want to, it's not going to change. But the question that I have is, what is the interior of A? So I don't know what I took, think about it carefully. So this is R, and I took some countable sequence.
Depends on the countable sequence.
Oh, that's the question. Does it depend? I'm asking you what's the interior. Oh, that's it. I didn't tell you which countable sequence I picked. So remember, I picked 1 over n at one point, and I saw that the interior of 1 over n in R was the empty set. Now, was there anything special about 1 over n? Can I pick another sequence? Will that potentially be any different?
The interior is just A.
careful, and this is R regular. It would be just A, of course, if it were the discrete set.
The null.
So think about it very carefully and think why. Okay, so how can I verify what's in the interior? So this is a countable set. I pick a point, just any point in that countable set, and I try to form a neighborhood. So could I make the neighborhood small enough to protect that element? Why not? Because any interval will contain how many points? Will contain necessarily, remember, every interval, open interval, is identical in some sense to 0, 1. You just expand it, scale it. So therefore, how many elements of R are in the open interval necessarily? Oh, infinite, yes, but how many? More specifically, as many as R, uncountably many. Do you see that? Think about it. Take any open set. You can just shift it anywhere. It's identical to the set in size from 0 to 1. And this set we showed by Cantor's diagonalization argument to be uncountable. So no open interval surrounding any point can possibly be fully inside of the set because the set only contains countably many points. Yep.
What if we switched it and we said instead of real numbers, you had A, the countable set of real numbers, and then our set that we were talking about would be like B, which is all the real numbers. What would be the interior?
Well, if again B is R, why do you need different symbols? So if you pick all real numbers, the interior with respect to R is R. The interior of every metric space within itself is by definition itself, because the open neighborhoods are selected as collections of the set itself by the very definition.
I don't think I'm asking correctly.
Okay.
But pick a new metric space
Pick a new metric space.
with on A, which is our countable set,
Okay.
and that distance.
And this is absolute value. So now this is my whole universe.
Yep. And then what's the interior of R?
Well, makes no sense because R is not, this universe does not contain R. It's only a part of it. So your question, when you speak about interiors, has to be this. You specify the universe and you specify a subset. You can only ask questions like this about the subset. If you want to, you can try to think, is there a way to make sense of what you're saying? But by what I described, this question is just not making sense, okay? You take the universe, and then you take subsets of the universe, and you ask, is that subset, what's the interior? So A interior, we concluded in this case, is A interior is empty set. Do you understand why? Because to contain an open neighborhood, even a single open neighborhood, you have to be uncountable set. One open neighborhood, here I'm holding it, it's the same size, it's the same cardinality as from 0 to 1, and therefore it's uncountable. And this set is countable, so the interior has to be empty. Okay, the set must be uncountable to have the potential of even closely being open, other than the empty set. Every set is uncountable that is open in R. That's like A interior, but what about the interior of A relative to A? So here I say my universe is A and I take the interior relative to that universe. What's the interior in that case? That's somewhat along the lines of what you were asking.
It's just A.
Yeah, it's just A, thank you. So you see, we're not even doing math, I'm just really just trying to teach you the language of what this thing means, right? How do you speak about interior and closure, and you have to drum it in your mind that it's a relative property. It's always with respect to what? Interior with respect to what? Because if it's a defensive set, what do you need to defend against? R? Here is, so just a moment, let's finish with this R and then maybe I'll ask one more question. So another question I want to know regarding that same sequence, if the sequence are if A, so if the sequence Rn is Cauchy, then closure closure of A, or a closure of Rn, is, so you can, is what? Is equal to, there are two possibilities. Either, what are the two possibilities? So I have a Cauchy sequence. So this countable set is a Cauchy sequence. So the closure of, so what can you say about, actually in this case you don't even have two possibilities, you just have one. What's the closure of that set?
A union limit point of A.
Exactly. And how many limit points?
One.
Only one. In other words, Cauchy in R means convergent. There is no difference. It's complete. Well, maybe we'll talk about it. I'm not sure I mentioned enough, but complete spaces are where there is no difference between Cauchy and convergent sequences. So it ends up being, every Cauchy ends up being convergent. So if Rn is Cauchy, so you can say that a closure is a union limit point. Some point R, where R is limit point. Okay? Make sense? Now, if Rn is not, can the limit points of a countable set be uncountable? Can I have uncountably many limit points? Not if it's Cauchy, but in general. If I have some sequence, can it have uncountably many limit points? So another question is, can a sequence of R, and of R I mean of course this R, the regular R, have uncountably many limit points? In other words, could there be a set that is just countable and I need to add so much more than the points in the set? If I have to add uncountably many points, could that happen? So, is that all your answer? So one person says no, rather confidently. Anybody else can says anything else? So you raise your hand if you think no. A sequence in R cannot have uncountably many limit points. 2 people, 3 people then. 3 people say that the answer is no. Does anybody say the answer is yes? Anybody has any other opinion? Voting is tomorrow. So the answer is, those that didn't raise their hands too bad. This is, of course you can. Just take Q. Q is countable. There we go. Ooh, we just saw it many times over and over, right? Q. So limit points of Q is R. Of course it's possible. Here is again, you have, what sort of sequences you have? You have the very bad sequences where everything is just everywhere, right? And you have the sequence that kind of, it all clusters. It's all the dust specks are in one region. It's Cauchy. Cauchy sequences are almost closed. All they need is maybe one more point added, right? Or if it's a metric space where they are clustering around nothing, then it's already closed, okay? But a sequence might just kind of cluster everywhere. Just have members here, have members there. So it can have as many limit points as you like. You can have 3 limit points. All you do is just interlace 3 conversion sequences. One going to this number, one going to that number, another going to another number. So you can have any finite number of limit points all the way to uncountably many, and Q is one example. Good, yes? What else did I want to ask you? Oh, one other example. So again, so now we take our M to be, let's say, R squared with the Euclidean metric, with the 2 metric. Okay, that's our M. And now I'm going to ask you this. So you take R. R is a subset of R2. You can just say it's x0, right? And then I want to ask what's the interior of R in R2. What's the interior? Yep.
Empty set.
Exactly, it's the empty set. Again, I'm trying to show this because R is very good to protect, the points on the line from being attacked from left or right, but it's not good at all in two-dimensional space. There are so many more places where this set can be attacked. Okay, R2, it's like the ants. They can form a good protection in the two-dimensional space, but a bird can fly and pick them up. So they're not good defenses in R3. Okay, so being open is relative, being closed is relative. You always have to know what's your universe.
If you use the one norm,
Yes, it's going to be the same. One thing about all those spaces, we showed that one norm, infinity norm, two norm, they're all the same. And let me tell you a secret, all the norms in a finite dimensional norm vector space are equivalent. They generate the same closed sets, the same open sets. So you can pick whatever norm you like. All right, good. And the closure of R is what the closure
R2.
So this thing, this line, it's horizontal, you're telling me it will eat it needs to eat every point anywhere in R2. Yeah, just draw a picture of it. Here is that line. So this is R, okay? And it goes anywhere else. Well, if I pick a point that is not on this line, so it's let's say above the line, is this a limit point of the line? Well, here's a neighborhood around it, so the answer is no. You see, it would be a limit point if I take this point and I draw concentric circles, and all those concentric circles contain some black segment of a line inside of them, but that's not happening. So, and if I do it below, right, so no point other than R is eaten, which means R is already closed. It contains all the limit points. It simply is R. What are the limit points of R? That's very simple. In R2, what are the limit points? R. If it had any more limit points, it will not be a closed set. Good? So those are extremely easy examples. I mean, right? Just get used to them, right? Maybe I didn't bother enough, but they are very simple. It's not.
Those are the easy ones.
I mean, again, you see, when you understand this class, you understand. My God, he is just kind of mumbo jumboing, just terminology. That's it, right? There is not a lot of math really. Just really, I'm just explaining to you. Well, what are the terms and ideas with which you work here?
So give us a hard one.
Oh, but for that we need to know, let's say we need to know more, right? We need to know, when you do complex analysis, let's say you might wonder, how many preimages does some open set have under some complicated map, for example, right? So then, and with those cases, so those ideas, they become much more complicated. When you study Julia, I can show you maybe. Well, I can show you what scares me at night, actually. Right? I might. So in terms of closed and open sets, there are two things I'm afraid of. I'm terrified of Fridays, and I'm terrified of pancakes. And I can show you why in a moment. since you asked what are the hard ones, right? Well, pancakes scare me. And also, just again, what we're learning in this class, that's why it's called Introduction to Analysis. We're just learning the very basic terminology to eventually maybe you'll do something with it. Can you say this? This is a pancake. This is a Sierpinski part. We actually are going to learn a little bit about pancakes of the sort, much easier ones, right? So you see this thing? The open set is basically the union of all those holes. Many of them are tiny, microscopic. There are countably many such holes. They're all open. And the pancake is, you can show there is this cell. You can deform it to something that looks like this, which I'm not sure about new cell phones. That's how your cell phone antenna looks like. If you open your cell phone antenna, that's what you have on the inside. Maybe I'll find you a picture. Well, here, can you see it? No, you cannot see it here. You can see it here. Okay. So this is a thing. I mean, this looks like an old phone. I haven't opened the new ones, but this is going to be called counter set. This is a two-dimensional analog of the counter set. We're going to learn the one-dimensional analog of the counter set soon. Okay. So that's coming. So it will get scary. And why did I open the projector is to ask you the following question, right? So the next topic, it's called nested interval theorem or nested set theorem. Maybe, what do they call it in my notes? For now, interval, but in general, it's the nested set theorem. That's important. Maybe I'll torture you with a question regarding this. Nested interval theorem.